But before I start, I know yesterday we had the first tutorial. So I want to get some feedback. I know Professor Vera spent a lot of time, and I also were discussing this because how do we make sure that we have this done? Because this is the one where we're going to learn a lot more. I'm kind of flipping slides. You're looking at what the material is, but when you run the, when you take that MATLAB code and break it down, like he did nicely, he was explaining how you split it into different parts, right? I think then you run it, in the process you would learn more, okay? So my question now is, how many of you completed what Dr. Vera mentioned yesterday? Okay, so problem 1 full, all of it, and you got similar results, right? The inverted pendulum? Okay. Up to the 3, okay. 2, okay. So, but then in the problem 2, there are several subs. You also completed that.
Sir, 2 cases we completed.
2 cases. Okay, so that you can do today. Right, I know. Sure. I think that's the right way to do it. That's exactly what we wanted you to do. So, go back to the slides and then cross-check the math, you put the dimensions. Otherwise, you won't understand what G had done. See, this is exactly what we want to do. I'm happy that. So at least you guys came in the problem 2 second part. So how about anybody else? Huh? So how far are you in the problem 1? So you done till 4, case 4, okay? Okay. Yeah. I think you want to. So my suggestion is, I want you guys to finish once you do the first problem, it's actually very easy for you to do the second one. The only thing is you may have to deal with the dimensions. But otherwise, I think it's the same process. It's a different system. It's the same process, right? So I think that's the only thing, but try to get it done today. Today afternoon we don't have any lecture, right? So I would encourage you to finish this today. This way, if you have questions, you can ask, number 1. Number 2, you remember the second tutorial. I think it's tomorrow, right? So we may get into some stability and beyond that. So this is why I think it's absolutely essential to understand how we are modeling that 10 CS, how the controller is working, you learn, you know what I mean? I think those kind of things you want to have definitely a good understanding. And remember, as we are moving along, we will get into neural networks. It's a little more complicated compared to the Q-learning. Q-learning is pretty nice, and it's a linear system, A and B, right? But when you get into neural networks, it's a little more complicated. And you have to deal with the activity, sometimes those problems. I think so. It was, I know, I think so. So I think, I agree, thank you for pointing out. There should be a code for intro to oral. That's what she was bringing it out. There were 2 problems we had. One is the policy iteration. That's the basic for reinforcement learning. I also encourage you to run it and understand that. Although in many of my lectures, I usually cover that without the NCS. Then I go, even today, I'm going to cover that. Neural network, activity. Then I would go into the actual. So there were some slides that were duplicated. Primarily I did that so that it's more like a recap. Okay? So I know many of you didn't have that background. So therefore, good thing I did to kind of duplicate so that I'm covering the same material, part of it. And this is without NCS. Then you basically get into the NCS. That's the only difference, right? So, but remember, it gets a little more involved because as we are putting more nonlinear system, linear system is much more easier. Okay? So, I think try to finish the intro to oral code. Make sure at least you run it. And make sure it works and you understand what's going on. And keep the slides so that you cross-check. That's absolutely necessary. This is one way you learn how those math equations are, or the code in there corresponds to what is in the slide. Okay? And then I think when we deal with the next tutorial, it's a little more involved. Okay? So that's one thing. And as we also mentioned, the assessment, they will be very similar. There will be different system, and you guys will have to do this. And within what, 2 hours? 2 hours. So make sure you're familiar with those, you know. It shouldn't be that hard, honestly. And that shows that how well you guys do. I know it's compressed, 2-week thing, you know, but I think if you do it, this will be a good course, honestly, a very good course. It could be more than one. You know, you have the neural network part and the machine learning side, and you have the network control system. That's what we were discussing with these two professors today. How can we make this? They are making revision in here. I'm positive when I go around, there are stuff going around. And the source code that I provided, even though it's not the way that I would like to see, but still, I think what Professor did was, he's kind of splitting it that essentially you could do that and have it as a curriculum in your campus. Yeah, right, that's right. So that essentially, and you know, I know everywhere these things are getting pushed. It's a big deal right now in terms of jobs. Okay? Any other questions, guys? Any other questions? Huh? Right. Okay, so that would be a design issue. So what happens is, so her question is that if you are dealing with NCS system, so I provided or we provided all those values like a delay, this and so forth. So how do you determine that? So one thing you need to do is, like when you are about to design an NCS system, first thing you need to know is what type of network you're going to have. Is it a wired network or is it going to be a wireless network? A lot of us prefer wireless. Okay? But wireless, there are challenges. Because wireless bandwidth is a lot less than a wired system, right? So you have to deal with that. Second, how many of those systems you're going to share on the same network? So let's say you have a batch reactor stuff running in a lab environment. Think about you have a wireless network. Under the same wireless network, you have multiple subsystems, right? A batch reactor, inverter pendulum setup. So then you need to realize that bandwidth will be shared. So when you share the same bandwidth, you're going to experience more delay. See? So ideally what you'd like to do is, you probably look at, okay, my bandwidth will be split by simple thing is average. So you take, if you have 4 systems, you divide that total bandwidth by 4, and then from there you compute the delay that you may have. Usually the network would give you an idea what is the maximum delay bound, usually, the type of network. And then you can look at it if it's wireless, usually the protocol will be IEEE, 802 or something like that, .15. If it is a wired network, Ethernet, you have a TCP/IP. So based on that, they give you what is the delay bounds. And once you know that, then you can determine what is the delay D-bar. So that D-bar is very important. And the packet losses, usually it's modeled as a Bernoulli distribution. That's what we did here also. You see? The Bernoulli distribution. And so once you, that's the only spec that you need. Also, the packet drops are always Bernoulli. The only thing is the delay, basically. What is the... so nowadays, I think it's a wired network, with this Ethernet, you have a pretty good bandwidth. Nowadays, I don't know here, but in the US, we are looking at like 1 gigabit, so it's quite fast. So I don't know here what is the, is it a Cat 8? I don't know what these cables are. IT people will be able to tell you, because the Cat 8 cable can go up to several gigabits. So that means that you are talking about delays are very, very small. You see? And so, but it's not just the delay, it's the combination, the delay and the drops is what makes it a challenge. Okay? Any other questions, guys? So, yeah, you can define. One is the cost. Remember that you define the cost. Actually, cost is the most important because when you define the cost, you are putting both the error as well as the input, right? So it's kind of combined. So you can actually define like other indices, right? The steady state error. You can also define the overshoot. You can add all those actually. You can do the settling time, the ones that we deal with in the undergraduate. Yeah, other transitions, yeah. And remember, in addition to it, there are other ones, like in the ITA criteria. Remember those? Yeah. But those need, exactly, those need these information like error and everything. So, I don't think we have anything you can use. Go back to your undergraduate, yeah. But the cost is absolutely necessary. The cost will tell us whether which one is better. Yeah. Because it combines both the state or the error, tracking error, and the input. Whereas some of the other ones don't consider the input. So you could have a higher input, but lower, better performance. But the input is also one of the criteria. We really don't have a whole lot of input, right? So I think that's very important. Yeah. Okay? Any other questions, guys? Any other questions? How about you? Were you able to get it? I know you had a version problem.
I saw the first term to guess.
You finished? Okay. So it worked. Okay.
So in the third cases, it was showing syntax error.
Right. Right.
And then in second column, I tried to.
So what did you do in the first one when you had the syntax error? How did you?
First two, there was no syntax error.
There's no first two parts. But how about the part three? I know you had.
For idea, there was showing the syntax error.
Right.
So I tried to find substitute. So there was IK and Lucati something kind of syntax.
Right, I know. I think that there doesn't work because the versions they updated some things. Yeah.
So I tried to solve with OD for different Lucati.
Right. No. You can't use OD. Right. You know what you should be able to do is maybe you can. I don't know. How do we?
No, actually, time being, you can share with.
Right, that's what I was thinking. Yeah.
And later on, he will update.
You can update your MATLAB. That's the other option. Yeah.
Here it cannot be done because
Yeah.
the MATLAB, your license version we are using, but it needs credential.
Right. I know you are not a student. You probably have access issue. Yeah, I know.
That is there.
Yeah. So you are using what version?
207.
117. Wow, that's quite old. Yeah. So this is a discussion we had actually, because the issue was always the versions. We can't plan which versions. So the most recent ones we can do. So yeah, maybe what you can do is you can work with one of them, and I think they're all staying in the same hostel. Yeah. Maybe you have to find some time talk to them. And maybe you can just see how you can at least run it. Yeah. I know you know MATLAB. It's just that you want to get that feeling that whether you're able to run and you can kind of cross-check those slides. Because I don't know, the other thing is how assessment-wise, what
We see because one she having some problem with laptop, so I told her okay, you can use my
Right. But we can't provide laptops for a lot of people. Like he is also same issue. I think.
we'll see that
How we can be done. I think we have a few. Otherwise, the people who are coming from outside is the main thing. At least luckily their laptops work, and he's the only one. Maybe this is what we need to think.
No, okay. For him, I can provide actually in my lab one PC is there,
Okay.
where advanced version is not
Yeah.
there. So on the time of exam, I can shift there to him.
I think that's all. Because the others shouldn't be having a problem.
No.
Everybody has, right? You guys have the credentials, so you shouldn't be having a problem. Yeah. All right. Any last question before I move on? Any last minute question? Yeah.
How can we optimize the rotation gain?
I don't think you can. There is no result that optimizes. But let me say this: the discrete time work we have done, it connects at least with the learning rates. Whereas the continuous time, There's no connection at all. So, like if you take a course on continuous time adaptive control, for instance, all those adaptation gain, you just say that it doesn't give you the bound. In discrete time, at least you have the bounds. So if you look at it, the learning rate, we have a bound. 0, alpha should be greater than 0 and less than something. But in actual continuous time, you don't have it. So, but you can optimize it. So you have to really. In other words, what it shows is for a range of values it would work. The question is, how do you pick a value out of that range? Is the question. I don't think we have a way to do it. In other words, there is no relationship, at least we could get, to either optimize it or whatever. I think it's a very difficult issue. At least I'm not aware of. Okay? All right. Okay, so I think we kind of still going ahead. So today will be lecture, we're looking at lecture 6. Okay? So you saw that we had 2 quantizers, we have a linear system, and we kind of went through some material about what is a traditional quantizer. And we also talked about the dynamic quantizer. Remember that? So what I wanted to kind of do today is we may want to look at the nonlinear system. This is linear. So in the nonlinear, I kind of covered quickly the neural network based optimal control. Because that's what I keep saying that. I keep going around and trying to cover that material. And if you remember this, you have x of k plus 1 is f of x of k plus this, and here is the value function. This is the cost to go, and there is a terminal constraint like we said, and n is the final time. So it's the same thing. So you write the Bellman equation. So the Bellman equation is the optimal value function at k to infinity or k to n is equal to cost to go, or from k to k plus 1, and then from k plus 1 to n. So it's kind of a recursive equation that you are trying to do. Okay? So in that code that I provided, you need the partial dynamics. If you remember that, you don't need F, but you do need G. So that's why I think she said that intro to RL MATLAB code, I think you should want to run that code. And it's shared by Professor Bera, right? It's shared. So I want you to run that. Okay? And then you have the one-time step ahead information is also needed here. You can see that is x of k plus 1. But how do you relax the G? So that's what's the fundamental issue. The only way you can relax G for a nonlinear system is explicitly you go with an identifier. So what does the identifier do? You remember, you write this equation f and G as a neural network because this is nonlinear. So write it as a neural network. It's a single layer because you only have one layer of x. And sigma f should form a basis. So you are expressing this, and then you are combining sigma f and sigma g. And so these weights are kind of combined. So you only need one neural network. So then you define an identification error between you assume the state is measurable. So you define the identification error x minus x hat, and that error is basically will be used to adjust the weights. So, but before you do that, you construct a augmented system with history. Look at that. X of k is xk, x of k minus 1 up to k minus f. So you're constructing the data and you're saving that data for the last few sampling instances. And you are building a vector x, capital X, and capital theta, and then you are constructing the set of weights, and you are doing this. Now, the purpose of doing this, now why are we constructing these delayed values? Can somebody tell me why?
Sir, we need to do this as
So why are we constructing? You remember that? We are constructing, that's my question. Why do we need that? Okay, what are you saying?
Sir, I said that we use those as inputs.
That's correct. But why? That's my question. Why do you need it? I think the answer is in equation 2. Why do you need it? No, there's no optimality there, right? There's no optimality there, but
Two is the update law. So
yeah, 2 is update law, just to update the weights.
So weight is limited to what?
So you see the update law. Update law uses the history. Remember that, right? That you guys understand. Why? Simple. You see the inverse, there is a term with inverse. That term is not invertible if you only take one instant of one instant. And there is a condition. What is the condition adaptive control? We did talk about it. I know some of you have taken adaptive control. What is the condition? Okay, you guys need to look at the slides. There is a condition called persistency of excitation. I did explain that. So the persistency of excitation condition doesn't satisfy if you're only taking one value at a time. So you have to construct kind of a matrix. And unless that condition is satisfied, that inverse that of the whole matrix doesn't exist. So that's the reason. The PE condition. So that's why I said equation 2. The equation 2 is, you remember this is a matrix. It has to be invertible. This can't be done unless you construct that history. Okay? That history makes that matrix invertible. That's basically what we call persistency of excitation. Okay? So, and you see that all this is also a vector based on the history. So this is also a different dimension than x of t, just like the NCs. Okay? So all this, a lot of people call this as data-driven control. Because you're using the data from the system and you're also saving the data also in the real time. All this is a real time control, right? So you have a buffer in the same processor and you are storing that information. Don't forget it. Okay? So the update law, you're generating the update law using least squares. And once you do that, then you get the update law and we prove that the identification error converges. Okay? So by doing this, once you have done it, then you can unpack this. You can unpack the W. And that W has both F hat and G hat, both F and G, okay? So then, now you're getting into the controller, like I explained yesterday. So the controller has to have two neural networks, one for the value function, V hat. So V hat uses another network weights, and you see that n minus k. So the basis function is varying, and for a finite horizon, it has to vary. So it's n minus k. N is the final time, k is the current value. Got it? So that sigma v uses not only the state vector, but also the time. Okay? So that is v hat, and then there is a terminal constraint. Remember I said for finite horizon you also have a terminal constraint. Okay? So, and then you construct the Bellman error. So the Bellman error is coming out of this equation that we talked about. So this is the Bellman equation, V star. So we use the same equation and construct the Bellman error. And so you see that Bellman error equal to you move that V hat from the left hand side to the right hand side, and we call that as a temporal difference error in reinforcement learning. Okay? So temporal difference. So temporal difference is because this is k plus 1, that is k, and there's a difference in time. That's why it's called temporal difference. It's just time-based error. Okay? So this EKB is the Bellman error, and you have the neural network stuff along with the cost to go. And then you also have the constraint error, terminal constraint error. Then what you do, you sum that up to get the total error, and then you have a update law for the weights, for the critique. So look at this weight update law. This alpha V is the learning rate. The learning rate for the critique. Okay? So what does the critique do? Critique approximates the value function. Don't forget that. So the word critique means it's trying to critique the performance, whether it's good or bad. In psychology, these things came from psychology. So like in a human brain, it critiques how well is the actor is going to do. So that's what it's doing here, okay? So basically you have alpha V. Alpha V is mainly the learning rate, and you see that sigma 1 and all that, and you use that total error to adjust the weights of this particular critique network. Understood that? So, yeah. Okay. Now, is it better? Still down? Okay. So that is the critique weights. This is how we are doing it. Now, somebody can raise this issue. How did we come up with the weight updates? Now, remember I said, what was the answer? How did we come up with these weight updates, either the identifier or this one? What is the process of arriving at these weight equation, update equation? How did we get that? Although I'm not showing you that, the derivation, what did we say? Lyapunov stability. So the book has the proofs. I think you may want to go back and look at it, okay? So all these update laws are basically being derived from the Lyapunov stability. You see? So if you don't use these update laws, there's no guarantee that your closed loop system is stable. In this case, uniformly ultimately bound. And why is it UV? Because you have approximation errors for the neural net. Okay? So you are doing that and you are showing that update law. Okay? Now you do the actor. So the actor is another neural network, and you see that there is one W hat of Q, n minus k, and then you come up with a error, action error or control input error. Control input error is generated by using two ways, U1 hat and U2 hat. U1 hat is basically the output of the network, actor network. U2 hat is generated by half or inverse. Look at that G hat. So I'm replacing the G with the G hat from the identifier. And then you're taking partial V hat over partial X of K plus 1. Even if I take partial V hat, I still need the G. You see? I still need the G. So you can make an assumption and say, I don't need a second neural network, I'm going to assume G is given. That's what I did in the intro to our code. Here we are assuming G is also unknown, and we are using an identifier. So totally how many neural networks here? 3 neural networks. You can implement it. As I said, we have implemented this on a mobile formation control of a mobile robot. It's published in our transactions on control technology. So you could actually show in real time, you could do that in 8086 processor. The only issue we had was memory, because we had 3 weights, the actor weights, the critique weights, and the identifier. So the storage was a problem, not the computations. And we have to swap. Remember, you need the old values. Remember, y hat of k plus 1 is w hat of k. So the previous value of the weights, you have to store them. And so that was the memory issue, the size of the network. And we had 3 networks. So computationally we are able to do it. It's basically the memory problems, because you have to swap when you are computing it. Okay? So, but you can implement it and then you can get that. But remember, what I'm using to tune this is basically used as the control input error or action error, U tilde. So whereas the actor uses the Bellman error, the critique uses the Bellman error, the actor uses the control input error. Now the question is, why can't we use the Bellman error for the actor? Why can't we do that? Now, how many of you took the adaptive control? I know several of you. There, you remember A and B. B uses U, update. A uses E. Yeah, the tracking error. Go back and look at it. Yeah. So if you look at the update clause in the traditional adaptive control, for A x dot equal to x plus du, updating A uses the track error, regulation and tracking error. The update for B uses the E cross product between E and U. Try it out. You can't use E because then it won't work. So the same way here we are using U tilde, whereas in the critique we use the Bellman error. Okay? So that is needed, and this is the only way we found. I don't think anybody, we came up with this, pretty much everybody using this. I don't think we have any better way so far. Okay? And you see that alpha u, this alpha u is the learning rate for this actor network. And so I don't have a way to select that. That's what the question earlier. But you can select using some trial and error. So here is the flow chart, pretty much. So you have an identifier. You can see you start with initial value and initial admissible control, U naught. Then you have the identifier with the update class that we just showed you. Then you have the value function, V hat, and its update class. Then you have the action network, U hat, and its update class. And then what you are doing is you are checking whether you reach the final time. And if it's final time, you stop. If it's not final time, then you increment the time k equal to k plus 1 and you go back. Okay? So this is, so it has 3 neural networks, don't forget that. So this is nothing to do with NCS, but NCS is just uses the same thing, where we have the quantizer. I'm going to show you the quantizer. But before I do that also, we also has incorporated actuator saturation. So remember, we talked about saturation in the quantizers. We can also have saturation for the actuators. So a lot of times control methods do not consider the actuator limits. So what happens is the control signals are very large sometimes. If you don't choose properly your gains. But the actuator has limits. So sometimes it saturates, you have the same problem. So I'm going to show you as part of this how we can use the actuator saturation as part of the optimization. Okay? Any questions here? This is without just a simple actor critique neural network based control of the thinking system, like a robotic system and stuff. So here I think the example, here are the, you see that, how the bounds are. I told you the bounds for the learning rates. You see alpha v has to be between 0 and something, and alpha, this has to be between, this is the identifier, 0 and theta am, and you see that it also has some bounds. So what I mean is, those are given, the bounds are given, but it doesn't give you a specific value, how you select. You have to pick between the bounds. Okay, any questions here, guys? So there is an example, tooling robot, that's a very classical example. Okay, this robot, tooling robot is a feed system, and you have those values there, and you can, I showed you last time, nicely converges. So you see that there's identification error, when the identification error converges, then the system response converges and the control input also converges, oscillate initially, and nicely they are converging. And you can see also the Bellman error converges, showing that it is optimal, as well as the terminal constraint error. Okay? So unless the Bellman error goes to 0, we can't claim it's optimal. And that's why we want that. And the terminal constraint error also has to be going to 0, because see, this is a finite horizon case. Okay? So that's why we plot everything, and you guys can do the same thing from the code, okay? And here we show that the weights are bounded and converge. Okay? So now, what I'm going to do is, I'm going to extend this to output feedback, Then we go into the case of quantization, okay? Because we want to show you the state feedback and output feedback, and so that's what I was trying to tell you, okay? So output feedback is very common because in industry, not every state is measured in practical system. So typically the outputs are measured. Okay. So now I'm going to stop a second here. I asked you to tell me, educate me. Remember that? Just like I'm giving you lecture, I asked you to check a few things, right? As anybody has an answer for any of those questions I asked you? Huh? You need to speak aloud. I want you to, you remember I asked you a bunch of things. What's the difference between learning and adaptation? Okay, what else I asked you? Yeah, that's right. What happens when something is not controllable or something is not observable? And what else did I ask you? There are a few things, not one or two. Yeah, somebody wrote something. Yeah, let's look at it, what it is. It's very important. Huh? Yeah, what is FI? Yeah, we know FI. This is FI in the tooling robot. I asked you, what is the other class of systems that, I know non-affin is one example that she told, but non-affin is very generic. But there are other class of systems. Okay, and what else? What other questions? Yeah, why norm is always positive? Because we look at the norms. Everywhere we use the norms in the proof. So why do we need to study norms? Okay, what else? What else? Huh? Right. What is the difference between thank you. What is the difference between eigenvalue and singular values? Where we call singular values and where we call eigenvalues. Yeah, those are important. And what else? Okay, difference between stabilizing and optimal? Is it what we said? Okay, and what else? What is the other one?
Why do you need to check Lipschitz continuity?
Yeah, why do we check continuity, Lipschitz continuity? That's very good. That's a very fundamental question. Okay, what else? Yeah, I think, so anybody looked at any of these answers? Okay, which one? Right, right. That's what I am asking, yeah.
So, you can change with the control input. Physical can add some actuator there.
Okay, that's what I want. So, if system is not controllable, there's nothing we can do. The only way we have to do is physically change the actuator location or add an actuator. Okay? So remember, you're going to see this in industry all the time. Because the people who design, that's why I was telling you the mechanical people or somebody, aerospace, they design, but there'll be a separate group doing the control. So when you model the system, you check it and you realize it may not be controllable. So that guy doesn't understand controllability and stuff. It's our job. So then immediately we need to realize that we have to look at the actuator and check that location. Either you move the location or you may have to add an extra actuator. Typically we change the location. Okay, how about the observability? You can add the sensor. But you know what I would suggest? Change the location of the sensors. That's what is observability is. Because that means that, remember I said, that example I gave you, the physician in the 16th, 17th century was watching the stomach digest food. What in the kaleidoscope example, what you do, you watch that what's going on inside the kaleidoscope. So the same thing, that physical system is like a black box. The states are inside the system. You're only seeing the outputs as it projecting out, and you're watching through the outputs what's going on inside the, all the states, what's cooking inside. So if your outputs are not in the right location, that means they're blocking the view of the states. Practically, that's what it means. The only way you can do that is by changing the location of the sensors or a type of sensor. Sometimes a particular sensor may not give you that, so that's what you need to do. And this is another one. So I know most of you know how to check controllability, but you need to understand practically what does it mean. Any questions? Okay, so we got one answer. So we need a few more. Anybody looked at any more like singular values, eigenvalues? You check the norm? So you check the eigenvalues also? No. So what is the norm? Yeah.
Norm is representing distance.
Right.
Size or length.
Right.
Size or length and
Right. Right.
eventually it will be positive.
It's always positive. Yeah, that's right. So now, the benefit of a norm is, you remember in the weights and all, they're all matrices. So what norm does is it just squishes into a single variable. Okay? So it's kind of a like distance or some measure that kind of tells you if you have multiple variables in there, you know? So is there a vector, you can try it out, or you could do it with a matrix. So that's what we do in the proof. We show that the whole thing is basically as one item, and we show that the whole thing is bounded, rather than looking at individual. It is always positive. It's a bound. Okay? So it's always positive. It's magnitude. Basically, it's prevailing the magnitude. Yeah. Okay, what else?
So adaptivity learning.
Yeah. So what is the difference? Yeah, that I don't think many of people know. So what is the difference in learning? Even that controllability, you ask anybody, that's not the problem. Learning and adaptation, what is the difference? So adaptation is what I showed you, that update line, right? That is the adaptation. So what is the learning and adaptation? That's right. Learning is understanding how to do this. Doesn't matter what the adaptation comes in, right? But learning also includes, I'll tell you even more, learning also includes experience. Adaptation doesn't. So if you look at adaptive control, it uses the current value of the error. The learning, you saw that it uses the history and all other things. Remember? So like when I gave you that example, let's say you ride a bike. You remember I gave you the example, you're going from place A to place B, let's say from your hostel to the department, and there could be multiple routes. And so what you do is you're going on one route, let's say there's a construction going on. And so you have to use a different route, and you don't want to wait until something going on, construction like this. Otherwise you would wonder, how do you go? Let's assume that you're late to a class and you want to find a route. So that's basically, we talked about exploration and exploitation. So exploration, you're looking at, already you're finding different routes. And then you're trying to learn, you know, which route would give you which is best. And if one of them is blocked, then immediately you realize, okay, I can go with a different one. So a learning essentially uses the history and our experience. Remember that. Adaptation uses that information and tries to adjust. So adaptation is an instantaneous process. So there's a huge difference between learning and adaptation. This is just one of them, and we'll talk more. So this, a lot of times people don't understand, and so you wonder, why do we have to do the learning? So as a human, we learn, you know, implicitly we learn, right? Because you are using your experience. Oh yeah, I have to do this. That's your learning, and in the back of your mind, we always have that. Adaptation is basically using that experience you are trying to adjust. So you might have realized the same problem. Let's say you go to a different place, you do the same thing. Okay? Alright, any other things that, what is the difference? You know the answer? That's different, yeah.
So when linear transformation applied, then it only scales, but doesn't change its duration.
No, but that is the, okay, but that's the process. But I'm asking you, what is the difference between eigenvalues? Eigenvalues are defined for a matrix, okay? And you're talking about eigenvectors, right? Now, I'm not talking about eigenvectors, singular values. Well, if you diagonalize it, those are eigenvalues. Right, but what my question is, what's the difference between eigenvalues and singular values? Not eigenvectors and singular values. I understand. Eigenvalues give you the magnitude and vectors give you the direction. That was not the question. The question was between eigenvalues and singular values. And this is applied here to our work. That's why I asked you that, what's the difference? Okay, anybody has an answer? Okay.
Sir, I think singular values project the matrix.
And is there any eigenvalue for square, non-square matrix?
I think you may want to look at it. Yeah, that's it. He gave a hint. Take a look at it.
Sir, we can represent a matrix in a model matrix.
Yeah. But anyway, I would say he already gave a hint.
So
Eigenvalues are only applicable for square matrix, but singular values can be applicable for anti-cross matrix.
For any matrix. So that's the major difference. But take a look at it. Yeah. I think you may want to look at it. We might have studied, but we never pay attention. You know? So I think it's, and the reason we do that here is because the weights are non-square matrices. Remember that. All the weights of the neural network are always non-square. So this is the one reason why we do that. Okay? All right, guys. So let's go back to the observer stuff. At least it's important. At least we got some answers. We were learning something here. Okay, so you have that x of k plus 1 is this. Now what I'm going to say is, let's assume that x is not measurable. In the previous design, we assumed that x is measurable, right? The state vector is measurable here. If you remember here I am assuming that state vector is measurable. Okay? So now I want to relax that. So I want to relax it. So what I'm doing is, here you see that outputs are only measurable, y of k. And so I have to assume that this system is controllable and observable. Otherwise I can't do that. And then I also need to assume the norm of this G matrix is basically bounded. Doesn't blow up, okay? So now the first step is to design and observe. Okay? So the outputs are measured. So therefore I'm going to add and subtract a times x of k. Okay? So you could do that, a times of x of k. If I add and subtract, that subtracted value is combined with this nonlinear f. So f equal to the f of x minus a times x. So basically I'm not changing anything, right? Not changing anything. So once I get it, then a is selected such that it's Horowitz. This is not Horowitz, actually this is typo. No, this is not Horowitz. Discrete time, what is it called? In continuous time, we call that when the system is stable, all the eigenvalues are on the left hand. Then we call that as a Horowitz matrix. In discrete time, what is it called? There's an equivalent name. It's called Schur, S-C-H-U-R. So check that out. The same thing, but in Schur matrix, that means the eigenvalues are within the unit disk. So that's a typo there. So A has to be Schur because this is a discrete time. Such that A comma C is observable, and that's important. So now you write it in this form, x of k plus 1 equal to a times x of k plus the neural network to approximate plus the approximation error. Okay? So now I'm going to design an observer. So my observer is estimating x hat of k plus 1 is equal to a is known times x hat. So that's the initial state. You start with the initial known state, x hat plus the neural network. Now look at that. Neural network is using estimated state. You see that? The neural network is using the estimated state. Now go back here. The previous case. Here I'm using the actual state as part of the neural network input. So that's the difference. You know, you have to keep that very clearly. So in this case, x of k minus 1 or x of k used directly because x is measured. In this case, in the output feedback case, x is not measured. So the only thing I am going to use is x hat. You see the difference?
Why you have neural network you are using?
Why I use the neural network? Because F and G are unknown.
Okay, but here it is A and AD is not.
No, I think it's nonlinear.
Oh, nonlinear. Okay.
X of k plus 1 is f of x of k plus g of x.
Okay, it is written in the form of A of x square and A
You
of
rewrite it, that's right. You rewrite it first before you. And the reason is because you need to select A such that A minus LC is, so
that
sure
condition
whatever.
has to be
Yeah,
satisfied.
that's why you bring that A before you do the observer. So you do that, and then here you see that you are using that estimated state, and since f and g is unknown, then you have that f plus gu, and then L times yk minus c times x hat k. Yk is measured, c is known, xa hat is available, estimated value. So basically this is your observer, y hat is c times x hat. Okay? So you have to do this because A minus LC, L has to be selected such that A minus LC is on the left half of the poles of the observer has to be on the left half. So that's why we do that here, okay? So now state estimation error x tilde is x minus x hat, and if you do that you get this equation, and where you see that the AC is A minus LC is a closed loop matrix. So you select L such that AC is shown, basically is inside the unit disk for the observer. And then you have come up with this update law, and then you can show that things are bounded, okay? So that's the observer part. Now remember, observer gives you the estimated state, x hat. So this observer was not there, this was something we have developed long time ago. And the main purpose was, you are estimating the state in the absence of the system dynamics. That question. Okay? Alright. So next, so now you design the same actor critique. You have the U hat, look at that, U hat as X hat, everything is replaced X's with X hat, and action error, you see you have X hat here X hat again, and then the same thing with the control. So everywhere, wherever there's X, you are replacing with X hat. So it's a lot more challenging when the state vector is not measured, but still works. The design works, okay? So if you do that, here is the design. So initialize the system, you initialize the observer, you initialize the weights, then you update the observer, and then you update the identifier in order to get that weights, update the weights, and then you update the value function and critique. Only difference is you have the X, replace X with X hat, and also the control input. Now the proof changes. The proof changes because your inputs to the neural network is no longer the state measured X, it's basically X hat. So because of that, things change, the proof. So the proof gets more involved, and so it gets bloody, So, but the flowchart is there, and we can show the same thing, boundedness of the observer, boundedness of the critique, convergence of the finite horizon, optimal control. So you can prove all that stuff works. Okay, so you take a Van der Pol oscillator, a different example. A Van der Pol oscillator, x1 dot equal to x2, x2 dot equal to this, y equal to x1, you discretize it, and you can plot that. And the A matrix is given here, okay, and you can see the A matrix, all the eigenvalues are within the unit disk. So you show the observer errors converge, you show the system response and control input converges, and you can show the Bellman error converges, the terminal constraint error converges, the weights also converge. Now the only difference is between the output feedback, it takes longer for the Bellman error to converge. Why? Why does it take longer? Why does it take longer to converge? Huh? States are not measurable, so the system is fighting. So first thing it does is it makes sure that X and X hat converges. So until that happens, then you can't learn the dynamics. Then it's the controller is trying to learn the dynamics, you see. So there are so many things which are unknown. So first the state, then the dynamics. Once you understand the dynamics, then you basically is able to do the optimization. So this is why it takes a little longer if you look at the plots compared to the case where when the state vector is measurable. So remember that the more it's uncertain, it takes more longer, right? The same thing to human too. So that's the main thing here, okay? So this is the control design, and okay, so now I'm going to stop here. We will have that after coffee. It's correctly 11 o'clock, around 11. We'll take maybe a 5-minute break. So when you come back, then I'm going to show you the actual saturation as well as the quantization for nonlinear roughing system. Remember, we looked at the nonlinear roughing system. We also will look at, I think it's output feedback. Okay?